Hello, everyone.
Hello.
Hello.
Morning.
Hope everyone had a good weekend.
Yes, thank you.
Yes, thanks. I hope you too.
Oh, thank you. Thank you. I'm going to go ahead and get started because I've only got about half an hour. I've got to get some other stuff done. Here we go. Okay, so I'm going to talk about the addition of the behavioral components. So far we've been talking about the structural components. And now I'm going to talk about the addition of the behavioral components. So we start with a description of the structure. And what we're going to do is we're going to add to that a description of the behavior. So the structural description, generally speaking, will be a higher order algebraic theory. I have not treated the forecomprehension as a binder to make the conversation simpler. Typically, though, that would be treated as a binder, which is why we'd use a higher order algebraic theory. From the initial theory, we're going to produce a new theory. And so you'll notice that the new theory contains the old theory, and then it's got a couple of new productions, which are source and target. And then basically, these are going to be the rewrite rules. So there's an eval rewrite rule, which turns a star at into a p. Right? So the source is a star at, the target is a p. There's a com rewrite rule, which turns something like this. So a for comprehension up against an output into one of these processes where P, which is the continuation of the for, it is modified by substituting at Q in for Y in the body of P. And then finally, we have a source and target. We have a rewrite rule for the par, right? So if you have the source of a par, RP is going to be the source of R in parallel with P. And the target is going to be the target of R and P. So you see it just pushes the rewrite all the way through, just the way the com rule does. So we take a whatever theory you've given us structurally, we add the source and target for each, and then source and targets live for each of the different rewrites, and then you have a set of equations which tell you what the source and the targets are. Is that clear? Does that make sense?
In your definition, you have two equal signs. How?
What do you mean two equal signs?
For example, in first you have source eval p equal, and then a star at p, and then target eval p equal p.
Yeah, right.
So these are two expressions, right?
Two expressions, correct? Yes.
Separated by this, yeah, in the middle, this space.
Yeah, I can put a comma in there if that helps.
Yeah, just want to be sure that I'm not.
Sure.
Okay. Thanks.
Sure. Okay. All right. So there we go. So that is the modification to add the rewrite rules, and now we want to say what does that do for the logic? Essentially, we have a rewrite rule of the form. So first notice that every time we have a new left-hand side, we get a new kind, right? So we're going to have a kind called R. And the general shape is going to be that if I have an R, and we say of type E, the reason we're calling it E is because it's an edge, right? It's an edge in the graph, right? So edges have sources and targets, essentially. So it's an edge in the rewrite graph. So this is of type E, and we can refine the E's, right? Which is, you know, that the E's will be built up in the same way, right? Meaning that I can build up these things, right? So I'll have an E for this, I'll have an E for this, I'll have an E for this. So we'll get corresponding rules for that. So the general shape of the rule, so those will all be constructors, right? We'll have rules for E constructors, and then the general modality rule looks something like this, and I'll talk a little bit more about variations in a second. But if R is an E which is of kind bold R, then the source of R is type target of E, which is of kind P. So let's look at some examples. So if R is eval U, which is of type rewrite, then the source of R is possibly target eval U, right? That just means that we can possibly take this evolution. Same here. If R is of type com, which is a kind rewrite, then the source of R, right, which would in this case would be something that looks like this. So that thing is of type possibly target of com, right? So, and we know that the target of com in this case will be a type that looks roughly like this, and that's going to be of kind P, and similarly for par. And then in general, you have to have composition rules. So you'll have something that looks like this, which allows you to compose the edges in the graph so you can get paths. So hopefully that's making sense, right? This is completely algorithmic, right? There's no, whoever's typing, maybe they want to mute. Whoever's typing, maybe they want to mute. Who is that?
Stas, are you there?
Okay. So hopefully, go ahead.
May I ask about eval? So you're saying possibly target. Is this the case for eval that we can always evaluate?
But
I'm just thinking
it may be in par with something. So you might not take that step. You might take a com step, or you might take another par step. So the possibly means that, you know, there's non-determinism.
I'm thinking more.
You only get one rewrite in interleaving semantics. You only get one rewrite per, you know, per evolution.
You're saying if we have some par that we want to evaluate,
Yeah.
we will not able, maybe we are not able to do it. And
Well, what I'm saying is that if you have a giant par with lots of rewrites in them, you'll only do one of them at a time. In this semantics, right? I mean, there is true concurrency semantics, but yeah, and in the standard pi/row interleaving semantics, what you have is non-determinism as opposed to true concurrency. Right. So you might take this one, but you might have taken another one that was in the par.
I mean, you said that eval will remove the star.
Yes.
So I'm thinking that if we are evaluating any process, we will remove the star. I mean, we will do the one step.
No, no. This is what this is. Let me show you what I'm saying. Just getting some place to write stuff down. Okay. Okay. So in interleaving semantics, even though I can reduce here and I can reduce here, in one step, I only get to do either this one or this one. So possibly this one or possibly this one. We don't know which.
So when you're defining the rule for eval, I was thinking that this is only eval term. This is not the par.
No, but that's the point, is you don't know the context in which this thing is occurring.
Oh, I see. I see. And why you have a com and the par as
well, because par has to do with a situation like this where I have more than one reduction in a parallel composition.
I see. I see. So basically, you're specifying, as you said, this is like just for all term constructors. There is or possible reductions.
Exactly right. That is precisely it. Yes, right. Yeah. So that's if you look carefully at the semantics for pi and for rho, you find that this is how it's specified. Sure. No, thank you. Good questions. So now you can see that that we're getting all of the we're getting all of the rules, right? So we get all the structural rules, we get all the behavioral rules, and we get all the collection rules, and then we have rules for how to tie the recursive knot, because this is a two-level type decomposition, right? It's not, the recursive knot has not been tied. But once you tie the recursive knot, which is what these rules do, then you get these kinds which don't have parameters in them. still, this is a little detail we need to worry about. And then the other thing that we have to worry about is, as I said before, providing the negations. So there's a form of negation that has to do with context, and there's a form of negation that has to do with treat. You can treat possibly, or yeah, there's a connection between the modal operators and the linear implication. So there's a way to treat linear implication and linear negation in this context. So you get two flavors of negation. One has to do with being able to break something into context, and the other has to do with being able to take steps. And then finally, the final refinement is that instead of just having a possibly here, you can have a possibly with a context, which allows you to say what your probe is, which becomes interesting for a wide range of for bisimulation, basically. So you have context labeled bisimulations, which then correlates between the reduction style bisimulation or barbed bisimulation and the labeled bisimulation. Right. So there are two flavors of bisimulation. There's the barbed bisimulation and the labeled bisimulation. And when you can have the context here, you can automatically connect the two, which then gives you good substitution theorems, right? So in particular, what you get is that the bisimulation that you generate is a congruence, which means you can do, substitution in equations, and it means you can substitute terms that inhabit the same type, which is important if you want to do automatic program refactoring. So that's essentially it, right? We're I will lay out in excruciating detail all of those things in the paper, but now what you're seeing is how the whole algorithm works for a particular example. And we've seen that we get a wide range of interesting types, right? So we can say things like non-empty, we can do stack safe operations, where you never pop a, not stack safe in the sense of recursion or tail recursion, but is safe stack in the sense that you can check at the type level that you would never run pop on an empty stack, for example. So you wouldn't do that. You wouldn't have to write that condition in your code. You put it in your types. And we can do things like, where is it? Here we go. With the negations, we can do formulae like primes, and there are a wide range of other formulae that I've talked about. So the main point is that now you've got essentially a delineation of the full generated type system, interesting examples, and refinements that give you even more interesting examples, along with substitutability, and the correlation between the typing based semantics and bisimulation. And those are all the quality assurance that you can want, right? It's the gold standard, right? So the connection between the type system and bisimulation is absolutely essential. If you don't have that connection, you can't do program refactor. And without the negations, you can't do examples like the primes. And with the change in the containers, you can get interesting examples, like I said, with the safe stack operations and many others. So that's I believe, you know, we now, once I have written up the entire paper, that's enough to go ahead and implement OSLF. What remains is to do, like, so if we're talking about a situation like this one, you want to take a check like this and compile it into a native query language, you know, whether it's flower expressions or SQL expressions or GraphQL expressions, it doesn't really matter, but you want those, you want this check to be turned into a native query language so that you're not doing all of it in memory. That'll get you decent speed up for a wide range of search criteria. But you won't ever be able to do it into a query language that isn't Turing complete, and that's because in a setting like this, you have to do symbolic evaluation. So what you can do is you can come up with query plans, right? So the plan is driving the native query implementation, right? So the plan sort of says, okay, do this chunk in the native query, and then do that chunk in the native query, and then do that chunk, right? But the overall plan is kept in memory. So that's it. I mean, that's the whole kit and caboodle. That is, yeah.
Yeah.
Any questions?
This is very exciting. So you're probably you'll talk about more about by simulation, right?
Sure. Yeah, we can talk more about bisimulation. Yeah, yeah.
But I just want to ask you. You said that with bisimulation we can replace programs with the same type.
Yeah. So what I'm saying is you have to have a correlation between programs inhabiting types and bisimulation, right? So bisimulation is your notion of your effective notion of program equivalence, right? And if you don't have a correlation between bisimulation and types, then you don't have this substitutability thing, right?
I understand. So basically, you're saying with this connection, we can replace programs with the same types. Without that, we can have programs with the same types, but who knows if they are the same.
Correct. That's right.
Okay.
Yeah.
And when you say compile to some native native part, what would be the input to decide what to compile? On basis of what we can decide that?
So basically, if you have only structural checks, then that goes to the database. But if you have modal types, that you can't do that in the database.
So we will analyze the input for OSLF, and we will say this and this and this part we want to create the native layer.
So when we're looking at this, right, there's the type, that's the input, right? So we're checking to see, so we go and grab, this is our GitHub repo. This is a program from the repo. this thing you could implement just as an in-memory type check, right? But let's say that the repo is sitting on top of GraphQL, right? And instead of doing an in-memory type check, right, you can analyze T here and check to see if which parts of T are just structural checks. And the structural checks you compile to GraphQL, and the modal checks are the stuff that you do in memory.
I see. So we're basically doing some kind of indexing so that we can offload the structural information, so that we can load only.
Yeah, exactly. That's correct. That's exactly right.
Okay, this makes sense.
Yeah.
Yeah, I have a question as well about type. So
you got really quiet there, Raphael. Maybe you're away from the mic.
yes, let me do some settings. Okay, it should be better.
Okay.
Okay. Yeah, I have a question about the types. You said that there are types for channels and type for processes. I think it was few days ago. Isn't the type of a channel just the type of the process that will go through it?
Not quite. So you can see here exactly the kinds of things that you can use for channels, right? So I want to be clear that what this does is it tells you something about the structure of X. Right now, it doesn't say what data is flowing over X. It just says, if I were to look inside X and see what kind of structure it has, that structure would be dictated by this.
Okay.
Now, there are such things as channel types. There are things like sorts and channel types. We don't provide those here, right? What we're saying is that either we can tell you about the structure of the process, right? Is it a for comprehension? Is it an output? Is it a parallel comprehension? Or we can say things about the evaluation of the process. Can it possibly go from the current state it's in to a new state which satisfies a new condition? Right. Those are the kinds of things we can say. So that's at the level of process, not at the level of channel. Now we could add channel types, right, which say I'm only allowed to see on this channel certain kinds of data types, but this system doesn't provide that.
Okay.
They're modular, so you can do both. Okay. Any other questions?
With this model, possibly operator, can we think about that as like catching all possible evaluations, because it's possible, and then we will refine it. We will have like more refined kind of these. So I'm thinking, for example, some kind of, this will always evaluate, some kind of type that we will say, instead of this diamond, we will say, always.
Yeah, you can have a there's a one called necessity. So dual to possibility is necessity, and we get the dualities as a part of. Yeah. Yeah.
So when you say diamond, you're automatically saying all other like.
When you say diamond, you're saying that there's one of them, and when you say necessary, you say that all of them. And necessary is, so necessary is usually written as a box as opposed to a diamond. And that means that all possible ways out of here end up in something matching this spec here. And you get that as a De Morgan dual. So there's a negation, which will, the negation of possibility will give you necessarily.
But you're also thinking about specifying some formula to say in these cases, right? As a type.
Well, again, you can do implications, right? So in your formulae, you can do implications. So there's it once you have a negation and a conjunction of some kind, right? Then you can do implication, right? That depends on your container semantics, right? So whatever your container semantics are here, then you can build up various notions of implication. And so you say, you know, A implies B is a formula, right? That's like the arrow type in functional programming. And once you have those kinds of things, then you can say, under these conditions, necessarily blah, right? So you can do rely guarantee kinds of things.
I see.
Cool.
Yeah.
Any other questions? All right. Thanks very much. I appreciate your time and attention. And yeah, I'll see many of you in the dev stand up in just a few minutes.
I'm so great. I'm so great. Can you share these pictures, these things?
Yeah, I will for sure.
Yeah. Thanks.
All right. See you soon.
Thanks.